The structure of the atom. The first theory was given by John Dalton, and he said that the atom is the smallest indivisible particle present in nature. According to him, atoms of different elements would weigh different from each other. So all oxygen atoms would have the same weight, all hydrogen atoms would have the same weight, but when hydrogen and oxygen are compared to each other, they will have different weights. Also, if these atoms were to combine with each other to form chemical compounds, they would combine in simple whole number ratios. Alright, eventually Dalton's theories were proven wrong because people started discovering subatomic particles, people started understanding the concept of isotopes. Cut to cathode ray experiments. What we do is we take a glass tube, and inside that glass tube there is a gas at a very low pressure, and we apply a very high voltage onto that gas. It allows the gas to conduct electricity. A discharge happens through the gas. Now, when this discharge happens, we notice that there are certain particles or beams that move from the cathode to the anode. These beams are known as the cathode rays or cathode ray particles. Eventually, when we experimented with different gases, we realized that this beam, this particle, exists in every gas, which implies that it's a fundamental particle of nature. We eventually called it the electron, and a negative charge was attributed to it. Similarly, the anode rays, which would move from the anode to the cathode, these were the positively charged particles. So we took the lightest anode ray and eventually called it the proton, which has a positive charge. People started doing a lot of experiments to determine the mass and charge of proton and electron. And once that was done, we realized that the atom has something more than protons and electrons because the numbers just don't add up, which led to the discovery of the neutron. Finally, what you have to remember is these values. Mass of the electron, 9.1 into 10 to the power minus 31 kilograms. Mass of the proton and mass of the neutron are almost equal, which is 1.67 into 10 to the power minus 27 kilograms approximately. The charge on the electron and the charge on the proton, their magnitude is exactly the same. The signs are different. Electron has minus 1.6 into 10 to the power minus 19 coulombs, whereas proton has the same amount with a positive sign. Now that the subatomic particles were discovered, people started working on different models of the atom. The first notable model was given by J.J. Thomson, which we all know as the plum pudding model, where you have a positively charged sphere with negative electrons embedded in it, like a plum pudding or a watermelon with seeds. Then comes the very famous Rutherford's alpha scattering experiment, where they took a gold foil, a very thin gold foil, and bombarded it with alpha particles. These alpha particles are essentially positively charged particles. What was expected was that if these positive particles hit the atom, these would deflect backwards, because the atom, according to the plum pudding model, was a positively charged sphere. But something really surprising happened. Majority of these alpha particles just went straight through the foil. Only a few got deflected and a very few actually came back. This meant that most of the atom is empty space. This led to the discovery of the nucleus, and Rutherford said that the nucleus is present at the center of the atom. It's very small when compared to the size of the atom, and it contains all of the positive charge of the atom and most of the mass of the atom. Rutherford also said that the electrons are revolving around the nucleus via electrostatic forces, but according to Maxwell's theories, this model of the atom would not be stable, because electron, being a charged particle, if it is revolving around the nucleus, it would continuously lose energy in form of radiation and eventually just fall into the nucleus. Science kept on developing and a lot of perspectives kept on changing. There came a time when people stopped thinking about light as just a wave with frequency and wavelength, but they considered it to be a particle. Max Planck was the scientist who suggested this, and he gave a theory that light carries energy in form of small discrete packets. These packets are known as quanta, singular quantum, multiple quanta. The energy contained in one quantum of light is equal to h times nu, where h is the Planck's constant, which is equal to 6.6 into 10 to the power minus 34 joule seconds, and nu is the frequency of light in question. This theory was applied really well in the explanation of photoelectric effect, which was given by none other than Albert Einstein. He took a very old experiment of photoelectric effect where scientists had observed that if you throw a certain type of light on a metal, electrons come out of the metal. Einstein explained this using the Planck's quantum theory. He said that there is a certain amount of energy that the metal requires in order for its electron to be uprooted. That energy can be provided by quantum. Yes. So if one quantum is bombarded onto the metal which has energy, let's say E1, the minimum energy required to uproot one electron from this metal is, let's say, E0. E1 minus E0 is equal to the extra energy we have provided. This extra energy will be equal to the kinetic energy of the electron. E0 or E0 is also known as the work function, which is essentially the threshold energy. The frequency associated with threshold energy, if we write E0 equals to h nu naught is known as the threshold frequency. Photoelectric effect is observed only when frequencies greater than nu naught interact with the metal. Pretty obvious, pretty simple. Then came the idea of atomic spectra. Take a group of atoms, shine a lot of light on it. What will happen is that these atoms will absorb few wavelengths from this light and then get excited because they've captured the energy from the quantum. Now, once they release those quanta back, once they release the same wavelengths that they had originally absorbed, they come back to their ground state. These energies that they release make the emission spectrum. The initial light without these wavelengths is known as the absorption spectrum. And if you can put two and two together, you would understand that emission spectrum plus absorption spectrum essentially gives you the original light source. The fun thing about atomic spectra is that it is unique for every different atom, which means that you could simply recognize a hydrogen atom looking at its spectrum, which led to people studying more about spectra. This idea was studied first by this scientist called Balmer. He gave us a formula for spectral lines of hydrogen in the visible region, but eventually Johannes Rydberg made the formula more universal, and this is what it is. The wave number of a line in a hydrogen spectrum is equal to 109677 into 1 by n1 square minus 1 by n2 square centimeters inverse. This 109677 centimeters inverse is known as the Rydberg's constant in terms of wave number. Please make sure you take care of the units. Now, once these spectral lines were established, once humans knew exactly what there is inside the hydrogen spectrum, you had the Lyman series, Balmer series, Paschen series. This data on spectra inspired Niels Bohr to come up with his own model of the atom. The caveat of Bohr's model of the atom is that it is applicable only to one electron systems. For instance, hydrogen, helium positive, lithium 2 positive, etc., etc. The Bohr's model features a nucleus and multiple orbits around it. The electron, the single electron that we are talking about, can exist in any of these orbits depending on how much energy it has. Yes, the formulae that you should remember for the Bohr's model of the atom are: number one, the quantization of angular momentum, mvr equals to nh by 2 pi. The other formulas that come after a lot of calculation of electrostatic centripetal force using the quantization of angular momentum are: energy is equal to minus 13.6 z square by n square electron volts per atom. R, that is the radius of the orbit, is equal to a naught n square by z, where a naught is equal to 52.9 picometers. Velocity of electron in any orbit would be 2.18 into 10 to the power 6 z by n meters per second. In all of these formulae, n refers to the number of the orbit and z refers to the atomic number of the system in question. The negative sign on energy's formula is just a convention. It simply implies that mathematically, when the electron comes closer to the nucleus, the overall system becomes lesser in energy, hence more stable. Now we started moving towards the modern ideas of quantum mechanics. De Broglie gave his hypothesis that not only light, every particle can be considered as a wave. If a particle is in motion, its de Broglie wavelength can be written as lambda dB, which is equal to h by p. Then came Heisenberg, and he said everything is uncertain. He gave us the uncertainty principle, which changed all the perspectives of how we look at things. Nothing is definite anymore. Everything will be talked about in terms of probability. He said that the momentum and position of a particle can never be determined simultaneously to full accuracy. Delta x into delta p is always greater than or equal to h by 4 pi. Then came the Schrodinger's wave equation, h psi is equal to E psi. If we put the Hamiltonian operator onto an electronic wave function, it would give us the energy of the system. Yes, now this equation being very complicated, we'd rather just remember the results of it for now. This equation gave us something called orbitals. Orbitals are regions, volume spaces in which the electron has the most probability of being found. You can say that orbitals are basically the houses of these electrons. Then we became acquainted with the idea of quantum numbers. These quantum numbers essentially give you the address of the orbital. The 4 quantum numbers are n, the principal quantum number, ranges from 1 to infinity, it's just a natural number. Then comes L, which is the azimuthal quantum number or secondary quantum number, and this can take values from 0 to n minus 1. Then comes M, that is the magnetic quantum number, and that can take values from minus L to plus L. Then comes the spin quantum number S, and this could take values minus half and plus half. L values of 0, 1, 2, 3 can also be called SPDF. We all know that. Then came the ideas of electronic configuration, and in electronic configuration we have 3 rules we need to follow: Aufbau principle, Hund's rule of maximum multiplicity, and Pauli's exclusion principle. Aufbau principle says that you have to fill these orbitals in terms of increasing energy. The idea of that could be obtained from the n plus L values for these orbitals, and hence it is also known as the n plus L rule sometimes. Then came Pauli's exclusion principle. According to that, you cannot fill one space with more than one thing. Pretty obvious, which implies that one orbital can have a maximum of 2 electrons. Then comes Hund's rule of maximum multiplicity. You have to fill 1, 1, 1, 1 electron in all of the orbitals belonging to one subshell before you start pairing them. Make sure you remember the exceptions in electronic configuration, that are chromium and copper. Alright, then we move on to psi and psi square. Psi is nothing but a wave function. It can be plotted on a graph. And if you take psi square, it gives you a graph of probability density distribution. Yes, so if you take a psi square graph in 2 dimensions, it will tell you at what distance from nucleus what is the probability density in an atom. So extrapolating these graphs into 3 dimensions gave us the shapes of the orbitals. Make sure you remember the shapes of the s orbitals, p orbitals, and d orbitals properly. F orbitals are a little more complicated for us at this stage. Finally, let's talk about nodes. Nodes are regions, volume spaces inside the orbitals where there is no probability of the electron being found. Obviously, at 0 and at infinity, there won't be any electrons. But these two are not counted in nodes because these are just implicit. These are common sense. Apart from these, if any region exists where there is no electron to be found, that region is known as the node. Nodes are of 2 types: radial nodes that occur along the radius, and angular nodes that occur at an angle. The formula for the number of radial nodes is equal to n minus L minus 1. The formula for number of angular nodes is equal to L. So the total number of nodes in any orbital becomes n minus 1. Alright, so that was the structure of the atom in 15 minutes or less. I'm sure this would have helped you. So hit that like button, leave in a comment, share this with your friends, and don't forget to subscribe. See you soon.